We learn about the big O notations. We learned that one problem can be solved with many ways. We only have a very simple problem, which is prefix averages, but there are three possible ways to solve it. I think in the assignment, it is also the same. Okay, you have one problem. Every student will have different way to solve it. So please make sure that you do not copy and paste from your friends. Okay? And yeah, you can do something like this one to check whether your algorithm is good or not. Okay? For the first assignment, I think, yeah, I do not put the requirement like the efficiency of your algorithm. And yeah, for maybe the next assignment, I will not also ask that one, but for your team project, okay, it will be important. So you need to find what is the best performance to solve your problem. In the big O notation, we have some relatives. Relatives here is like the family of the big O. So there are other variants of big O. Yeah, we call it big omega and big theta. In the big omega, yeah, this is the requirement. Fn is big omega Gn if there is a constant C greater than 0 and an integer constant n0 greater than 1 such that Fn is greater than equal to C multiplied by Gn. If it is the big O notation, the Fn is less than equal to C multiplied by Gn. Okay, but if it is big omega, it shows greater than or equal to. What about big theta? If it is a big theta, then we have the Fn is big theta Gn if there are constant C prime, which is greater than 0, and C double prime is greater than 0, and an integer constant n0 is greater than equal to 1. What we can say here is the C prime multiplied by Gn will be the lowest one, and the C prime multiplied by C double prime multiplied by Gn will be the higher term, and the Fn will be limited by the C prime and the C double prime. In easy way, okay, please do not confuse with this complex definition. In easy way, you can see like this one. The intuition for the asymptotic analysis or the asymptotic notation, if it is big O, Fn is OGN if Fn is asymptotically less than or equal to Gn. If it is big omega, then Fn is asymptotically greater than or equal to Gn. If it is a big theta, Fn is asymptotically equal to Gn. That's the intuitive way to define the big O, big omega, and big theta. Now, let's just check with these three examples. 5n power of 2 is big omega n power of 2. Yes, it is true. The same with the big O rule, okay? Because it is still a Fn greater than equal to Cgn. Okay? Because it is the n power of 2, big omega n power of 2. Then it is still true. The second one, 5n power of 2 is big omega n. Then it is still true. Okay, you can try with this mathematical notation and you can find a proof, and there will be a proof C equals to 1 and n0 equals to 1. So the C multiplied by Gn, because it is the big omega, the Fn is still greater than equal to Gn. C, which is a constant, multiplied by the Gn. Then this condition is true. What about n, which is 5 multiplied by n power of 2, is big theta, n power of 2. Yeah. By intuitive, this notation should be equal if it is big theta. Then yeah, this is true. Okay. So there might be a kind of questions in your exam. If I give you this kind of notation, check whether it is true or false. Then you can see how we can prove it, whether it is true or false. So I gave one other example. If we have the Python code and how if we need to check the operation. Okay. I hope by now you can understand the Python code and you can try to imagine. You can imagine that this code will produce what kind of result. So we have A equals to 5, B equals to N, C equals to 10, okay? And we have the I equals to range N, J equals to range N, and then we have X multiply equals to I multiplied by I, Y equals to J multiplied by J, Z equals to I multiplied by J, and we have the K will be until range N, and there's one equation, this equation. Okay, and we have this operation. So if you look at the primitive operation, yeah, this is primitive operation, primitive operation, primitive operation. Then, yeah, this is lower term, you can show. And then we have I until N. So there is no definition of N here, but we know that it is a loop. And the operation will take N time. And then we have another for loop N. It means after we finish this N, there will be another N. Then it will be N multiplied by N. What about this? Do not confuse with this multiplication. Even though this is a multiplication, but it doesn't mean that you will have a n multiplied by n multiplied by n. Okay, it is just a primitive operation inside the loop. So you don't need to care about this one. Even though the multiplication is showing like this one, but it is just a primitive operation. It is also primitive operation. This is also a primitive operation. Then you will have still n multiplied by n, or n power of 2. And as you know, in Python, we have the indentation, because this indentation, we can see that the for inside another for. Once we finish, okay, we have another for loop, but it is on the left. So it will run again from the index 0 until n. So it will take n times. And this equation is just primitive operation. This also a primitive operation. So overall, it will be n. What about this? Yes, this is also a primitive operation. Then we can just drop it. In overall, we can get like n power of 2, which is the higher term, and we have n, which is the lower term. And as we learned before, we can drop the lower term. Yeah, if you want to calculate one by one, you will get like this operation. You will get this notation for the mathematical expression. But at the end, when you need to write the big O analysis, so if I give you this code, and if I ask you, show the big O analysis, and you can just show this one. Okay, O n power of 2. That will be enough. Because sometimes you may have different things about the operations. As we learned before, the lower term can be dropped. The constant can be dropped. So yeah, why do we need to consider those for the big O analysis? Yeah, it is not important. We want to know only the worst case analysis. Okay. That's the chapter about the algorithm analysis. Now let's move to the next chapter. So I already posted into the e-class about recursion. We are going to learn some recursion patterns, and yeah, we will also learn what is the meaning by linear recursion, and there are some recursion variants. Recursion pattern. We need to understand the pattern, and we need to understand the definition of the recursion. What is the meaning by recursion? Recursion is when a method calls itself. So the classical example for this recursion is loop function. If you understand loop, you can understand recursion. The recursive definition, Fn equals to Fn minus 1. It might be strange to understand this one, but we can take a look on this code. We have def, it is a function in Python, and let's say I have the name countdown, and I have one parameter, I. I would like to print I, and then I would like to call the function countdown. So I call the function inside that function. That's what I call as the method calls itself. So it kind of look, yeah, when I equals to 3, for example, I will call the countdown again, but now the parameter will be I minus 1. So it will be 2. It will count down, it will go to this function, count down 2, and then print 2, and then count down I minus 2. So it will be 1. So 3, 2, 1, and then it goes down by 1, by 1, by 1, by 1. It will be infinite loop. Okay. So the recursion, we need to have base. We call it recursion pattern with base. What does it mean by base? A Python method with base shows that whenever we have a function, there should be a stopping criteria, or there should be a stopping condition. I would like to print n, and if n is less than equal to 1, return or the stop. If not, count down n minus 1. So let's say if I put n equals to 3. If n equals to 3, I will print n, I will print 3, and then it will check. N is less than equal to 1? No, 3 is still greater than 1. Then we will do the countdown. N minus 1. Then it will call 2. So it will go to this function again and then print 2. N less than equal to 1? No. Then it will go here again, n which is minus 1, then it equals to 1. So again we call countdown 1, print 1, n is less than equal to 1, yes, then return. When it returns, it will go back to the when the n equals to 2, because there is no further statement, then it will return back to this n equals to 3, and there is no further statement, then stop. That's the way we see on the recursion pattern. The formula will be something like this one. If n is less than 1, that's empty. And if it is not less than 1, let's make it minus 1. Okay. So I gave you, this is a good website to see if you want to try. This website can visualize the step. So if you want to understand, you can start visualizing your code now. So let's see, I want to make this pattern. Okay. Def countdown n, and then I would like to print n, and then if n is less than equal to 1, and then I would like to return, else countdown n minus 1. Okay. And after this, you can try with countdown. Let's say I call 3. you can visualize your execution. Now we are in the position of the red. Let me just let me enlarge this one. Okay. Now we are in this position. You can see there will be like 17 steps, and you can click next. So when you click next, because it is a function, it will not be executed until you find the statement to call the function. So here is the code to call the function countdown, and we have 3 as the parameter. So if you go next, now we call countdown, and then n equals to 3. If you go next, okay, we are going to print n. So we print 3. And then if, maybe it will check n less than equal to 1 because it is 3. So it's false. We will go to this statement, countdown n minus 1. Countdown n minus 1. Now n becomes 2. And then print n, we will print 2, and then check n less than 1. No, we will do countdown n minus 1. So n minus 1, it will be 1. And then we call again the function countdown. Again, we will print n. Now it prints 1. Check n less equal to 1. Yes. So we go to the next. Return value. And we can say this is finished. And let's go back when the n equals to 2. Because we already finished, then it returns value. And then we go back to the n equals to 3 because we finished this one, and it will return the value none and stop. So that's the step by step to understand how the Python runs with this recursion. As I mentioned to you before, in the recursive method or the recursion, some literatures call recursive, we can say recursion. There are 2 things that you need to understand. The first is the base case, and the other is the recursive calls. The base case means the values of the input variable for which we perform no recursive calls. So it means this is the stopping. There should be at least 1 base case. If you don't have the base case, it will be infinite. Every possible chain of recursive calls must eventually reach a base case. So there should be 1 time to reach the base case. Recursive calls. The recursive call means you need to call the current method. So in our example, the method name is countdown. So we will call the countdown method. That's what we call as the recursive calls. And its recursive call should be defined so it makes progress toward a base case. If the condition is less than equal to 1, it means the parameter n should go to 1. Now, we have another example. Factorial. I don't know what is the Korean name. Okay. Factorial means we want to multiply. If we have n factorial, it means it will be 1 multiplied by 2 multiplied by 3 multiplied by any value until n. Okay. This is also a loop, or this is a kind of recursion. We can use it. You can use recursion. Let's say if I have an fn, then the recursion will be n multiplied by fn minus 1. It will be 1 when n equals to 0. Okay. We know when n equals to 0, so 0 factorial equals to 1. Okay. So when n equals to 0, let's make it 1. We can define the factorial here, and then we have n equals to 0 returns 1. If not, then we will do n multiplied by factorial n minus 1. So this is the visualization. Okay. If you want to see this one, okay, but let's see from the Python tutor. I think it will be good to see the step by step. This kind of simulation will be interesting. Factorial. Okay. I have the factorial n, and then if n equals to 0, so we call this is the base case. If n equals to 0, then returns 1. If not, then return n multiplied by factorial n minus 1. We can call factorial and put any number. Let's say I have only 3. Okay. I would like to visualize it. So Python recognize this is a function. Now we call 3. So the n equals to 3, and then n equals to 0. No. Then it will go to this statement, n multiplied by factorial n minus 1. So 3 multiplied by factorial 2. Because we are calling the function factorial 2, what we will do is doing the function first. N equals to 0? No. Then again, we will do n multiplied by factorial n minus 1. So it goes back to the function n equals to 1. Now check n equals to 0? No. Then we will do again n multiplied by factorial n minus 1. Now n equals to 0. So the condition is true for n equals 0, and now it returns 1. When it returns 1, so the return function, the return value is 1. When it returns 1, how can we return it? This return 1 when n equals to 0. So the 1 will be multiplied with n equals to 1. And then it will return value 2. Oh, it will be 1 multiplied by 1. So now it will be 2, because 2 multiplied by 1, it is 2. It will return the 2, and then it will return 6 because we have 2 in the previous one. 3 multiplied by 2. And at the end, we will have 6. So the return value is 6. Maybe I can x equals to this one, print x. It will be easier to see the result. So if you go to next, okay, let me just skip. You will see 6. Okay, because the return function, it will not give any effect before you assign to a variable. Okay. So this is the recursion trace. So this is the same what you already saw on the visualization in the Python tutorial. Now this recursion can be done in any kind of problems. For example, searching. When you want to search a number in a list, what will you do? If you want to find number 22, the common method to search is to start from index 0 and go to the next index consecutively. Suppose I have this list. Okay. The list in index 0 is 2. The value is 2. The value of index 1 is 4. The value of index 2 is 5. The value of index 3 is 7. Maybe if you write in the code, in the Python code, list 1 equals to 2, 4, 5, 7, 8, 9, 12, 14, 17, 19, 22, 25, 27, 28, 33, and 37. Okay, we have the list. The question is, find where is the index of 22? You will write the code something like this one. Find n, which is the value that you want to find, and the data. So if I want to call find 22, comma, this one, because I want to find the number, the value 22 in the list. Okay. Here we can do the for loop. For every I in the data, let's check if I is equals to n, then return I. Okay, yeah, it means I just want to return the value. Okay, I didn't return the index. Yeah, let's say, yeah, I will just use this one. Question is, how many operations do we have? Whenever we do like this one with for loop, we will start from the index 0. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, yeah, 11. Okay, let's say, yeah, it's about like 10 operations. Okay, 11 operations, 10 operations to find this number. So if we have like we have 16 data, then yeah, in the worst case, you will do 16 operations. That's the simple search function. However, how if we use binary search? I will explain a little bit this. Let's see the visualization first. Okay, it will be easier. In the binary search, we consider 3 cases. When the target, okay, in the previous example, I want to find where is the number 22. So if I know the target is 22, so I need to check where is the middle data. If the target equals to the data in the middle, then we found target. If the target is less than the data in the middle, then we recur on the first half of the sequence. If the target is greater than the data in the middle, then we recur on the second half of the sequence. Let's see this one. I want to find the target, maybe, yeah, I think same, 22. I want to find 22. So first I need to define where is the low, where is the high, and where is the mid value. The target is 22. The target equals to the data mid. 22 equals to 14? No. Then we need to check. The target is less than the data mid. 22 is less than 14? No. 22 is greater than 14? Yes. Then what we can do next is just search from this one. We do not need to care this one. Okay. We do not need the left one. We only need the right one. So we can determine what is the new low, what is the new mid. And after we have this, again, we check. 22 is the same with the mid? No. 22 equals to 25? 25 is the mid? No. And then 22 is less than the data mid? Less than 25? Yes. Then next is we can just consider the data which is less than the middle value. What we can do next is to make a new low, or maybe the low is the same, and then the mid has been changed and the high has been changed. The same with the previous one, we need to check if 22 is the same with 19. No. 22 is less than 19. No. 22 is greater than 19. Yes. Okay. So we have the new value here. So in this case, the mid value is the same with the low and is the same with the high. Now the question is, how many operations do we have here? We have only 4. Compared to the previous one, we have like 11 operations, or yeah, 10 operations. Which one is better? Of course, this one. Whenever you make your algorithm, we want to find the better performance. You have only 16 data. It is still small. But when you have 1 million data, the binary search will work better. So let's see the code. There are 2 codes that I put here. The first code is using loop function. Maybe you will ask if it is a loop function like this one, then it might take n times because loop, we will do like from 1 until n. But don't forget, in the while loop, we can determine the condition. So this condition is, you can see one by one. We determine the low and we determine the high. And then while low is less than equal to high, then it is just to check. Okay. And then we want to make the mid value. The mid value will be the low plus high divided by 2. You still remember what is this division? We want to get the integer value. Okay. Do not forget with this mathematical operation. And your guess value, okay, your guess value will be the mid value. And if it is the same with the item, then you can just return it. If not, then you will check whether the guess is greater than item. If it is greater than item, then determine the new high. Else, determine the new low. And then you will check again here. It will be a loop until you return none. So if there is no such value, or it will be known if the low value is higher than high. With the recursion, you can see this code. We have binary search, we have the data, and we have the target, and we need to define the low and high. First, we need to determine the base. This is the base. So when you define this base, it means it is the same with the for loop that you have here. This is the base. If the low is higher than high, return false. If not, okay, you will make the mid value. After you make the mid value and you check. If the target is equal to the data mid, then returns true. It means you find the value. If it is not, okay, let's check. If the target is less than the data mid, do the binary search. Do the binary search. And we need to define what is the data, what is the target again, what is the low, and what is the mid value. Oh, sorry, what is the high value? If it is not the case, then we will go to this last statement, binary search, and the data, the target, mid plus 1, and high. So we will call again the binary search. This is a recursion. Okay. Okay, I guess it's the time to finish. I will explain more about this on Monday. Any questions?